Hi everyone, welcome to TensorFlow user group Mysore meetup, and we are one of the second biggest community in India, and we have events every week. So I would recommend go and follow or subscribe to our meetup page. And I also lead several communities other than TensorFlow user group like Google Developers Group and Vimal TS as well. So we have masterclass workshops coming up every week. So I'll just share the slide in the comment section so you can go and subscribe to these events. And if you're interested in volunteering or if you want to reach out to me for speaking at the events, you can contact me in Twitter. I've put my Twitter handle, it's U Rangaraju. And you can also reach out to a core volunteering head, Nikhil, and I've mentioned his email ID here. And the community partners for this session is Co-Learning Lounge and Applied Singularity. And we have shared the links in the description of YouTube video. You can subscribe to Co-Learning Lounge YouTube channel, and you can download the Applied Singularity app. They've got wonderful resources for data science, getting started with data science. Without much further ado, I'd like to introduce the speaker for today's session. His name is Rohit Ghosh, and he is a Google developer expert in ML, and he is also the founding member of Cure.ai. And the topic for today's session is AI in medical imaging. I'm handing over the session to Rohit. Thank you.
Hey, thanks, Usha, for that nice introduction. So, hopefully,
Yeah,
I'm audible right now, right?
yeah, you're audible. You can share your screen.
Yeah, I'll just share my screen. Just give me a minute. So, my screen is visible right now. Is it? Usha, can you confirm my screen is visible
Yeah,
at this
yeah,
point?
your screen is visible. You're good to go.
Okay,
That's
great. Thanks.
yeah.
So, firstly, thanks, Usha, for organizing the session. It's always good to be back in the community, although I don't get a chance as much often these days to interact closely with the community, and it's actually been a while. So, absolutely happy to be back and to talk with everyone who's there online. So, the idea for the session is primarily just to keep it a freewheeling chat about medical imaging and AI specifically, and focusing mostly on the journey that we have had at Cure over the last 4 years. Um, and primarily, any questions that you have, anything, just pop it up in the YouTube chat. I'm trying to keep a tag of that as well while talking. I've not done that before, but absolutely happy to sort of keep a look an eye on that YouTube chat as well. And any question that you have, I'll try either answering in between during the sessions if I think that might be easier, but else I'll probably try and take them towards the end of the session. So that's the outset. I think happy to just give you a sneak preview into what it takes to primarily build AI for medical imaging, and how that is sort of very different from AI for other computer vision problems, right? So that's the primarily context that I want to cover. So in terms of my background, so I mean, in terms of what Usha already mentioned, so I'm a founding member of Cure.ai. I'm a GD for ML. In terms of other things in data science, I'm also an instructor, author. I've kind of like forgotten 2 books that we already have on ML and that I've published till now. Apart from that, I have also YouTube lectures, which are currently completely freely available. So those are the lectures that I had done with Grey Atom, which is one of the leading data science institutes in Mumbai. So yeah, so primarily been involved in multiple things, and obviously, the most important obviously is what I've been doing at Cure since last 4 years. So there are 3 sorts of roles and 3 sorts of hats that I wear. So whenever I do a session, I try and detail down into one of those hats. So the first hat is obviously as an AI scientist. So as I said, Cure.ai is the AI for medical imaging company that we started back in 2016. And primarily as an AI scientist, I had been extremely involved in building the AI behind the head CT algorithm that we have, the AI algorithm that can look at a CT scan and can identify critical abnormalities from head CTs. So that's primarily my role as an AI scientist. I've been building that, published, I think around, I'm not sure again, would be somewhere around 14, 15 research papers, patents on that particular uh, entire product range. So that's my primary role, which is obviously the reason, and that's the hat that I'm going to wear for the talk today, which is primarily as an AI uh, practitioner. The second hat has been primarily as an instructor and author, so where you are not just doing it yourself, but you're trying to uh, take that learning what you have done in the first part and take it back to the community and make people understand, which I absolutely enjoy a lot. It's been one of my most favorite things, right? To take some of the concepts that we have and specifically the practical learnings, from building AI in a cutting edge field, take that and help people understand and get more and more people into the field. So that's my second role. And the third role is slightly, I mean, obviously as a founding member and a mentor for other startups in the AI space. Also, I've been primarily involved also in sort of mentoring other startups as part of Google Launchpad as well, right? So I've been mentoring some startups in Google Launchpad as well, and otherwise also. So it's more from a business angle and trying to understand what AI kind of, obviously AI is a research field, but also when you take it to a product and work it out as a startup, that's a different nuance altogether in how to actually build those kind of AI system, which is very different from how you do a research as an AI scientist. So there's a third perspective also which I have, but primarily for today's conversation, I think it's mostly, I think, as an AI scientist and mostly as an instructor, I would try and walk you through some of the concepts. That's the idea. Uh, so yeah, that's primarily the angle that I just wanted to give you an idea about. In terms of Cure.ai, as I mentioned, it's an AI for medical imaging startup. We started back in 2016, and as of today, we are almost across 28 countries. And there are primarily two major AI products. One is AI for chest X-rays, an AI system which can look at a chest X-ray. It can identify all major abnormalities from a chest X-ray. And the other one is an AI for, as I mentioned, non-contrast head CT scans, CT scans of the head, where you can look at the AI can look at the CT scan and then can identify all sorts of critical abnormalities. So those are the two major flagship products we started off with back in 2016, and today we are thankfully been present almost across 28 countries with a lot of presence across Southeast Asia and other parts as well. So yeah, somewhere around I think 10,000 scans that we are processing on a daily basis at some point in time, I think just before COVID. So yes, that's how Cure is currently positioned. So, but then the session today is primarily not obviously about Cure, but it would relate to the stories that we have had at Cure. So, the first part of the session is primarily about talking about why is computer vision in medical imaging difficult as opposed to computer vision in other parts of the spectrum. So, that's the first part of the session. The second part of the session would be how do we actually tackle some of those challenges. So, the first part is more about the challenges, and the second part we are going to talk about how we solve some of those challenges. So, in terms of challenges, the first challenge is obviously, non-standardized images. So, when I say non-standardized images, normally uh, if you're doing image processing for something like, auto driving car or something else, right, which is in the natural image, you fairly know the dimensions of the image, like a 256 image, and with a standard RGB channel image that you normally have. And yeah, that's the kind of, normally you have, at best you would have a single channel image, right? That's how most of your natural images are. There's not really a lot of variation in natural images, but in medical images that's absolutely not true. Unfortunately, in medical images, there's a lot of variation. For example, the first variation comes primarily from the size. So not all images are of standard sizes. So there could be a CT scan which could be a 512 plus 512. There could be an X-ray image which could be, for example, 256 or a 512 or a 1024 or even a 4096 plus 4096. So there are different variations in which just a single image happens. Now, the second layer of complexity comes from primarily that some of these images, like say a CT scan of a head, is not anymore just a single 2D image. It's actually a stacking of multiple 2D image, which is primarily makes it a 3D image, right? It's very similar to how you would process a video, right? But then that's not only the complexity, right? So some of these scans, like a head CT scan, would also MRI scan, for example, of the head would not only be a I mean, it's already a 3D image, but on top of that, you sometimes would have 4 or 5 or even 10 channels of them, right? So, whereas you have RGB as just 3 channels, in some cases like MRIs, you would almost tend to have 10, 15 channels of a 3D image, right? So, the layers of complexity just add on to top of what you normally would have in a natural image. So that's the first level of challenge that I would say you normally face. The second layer of challenges, and this is a very interesting problem. So for you to, for example, for me to first explain you what the challenge is, I'll have to first give an idea of what is a CT scan and how does it look, right? So as I've explained already, the head CT scan is a stacking of multiple 2D images, right? And whereas normal images, your pixel is an intensity value which can vary from 0 to 256, right? But in case of CT scans, the pixels that you see here, the images that you see here, they are actually not image intensities, but they're something called Hounsfield units. So Hounsfield units is primarily an indication of you know how well the tissue could primarily absorb that radiation. So different parts of the brain would have different level in which they can absorb, and hence the different parts would have different Hounsfield units. So, for example, Hounsfield units goes from, in case of CT scans, goes from minus 2000 Hounsfield units to all the way till 3000 Hounsfield units, right? So that's altogether range of 5000 Hounsfield units. So what you see here as image is actually, I mean, although we have translated it and transformed it to look like a normal 2D image where you can see the different parts of the brain, but in actual reality, these are not pixel values which are going from minus 2000 to 3000. So minus 2000 is the black area that you see outside the brain, and 3000 is primarily this extremely white area, which is primarily the bone part of the brain, right? So that's the Hounsfield units which differ, right? And the question obviously is that, okay, so Hounsfield is very different, and it's very different. I mean, it's in essence very different from not natural images where you have 0 to 256. The question then that becomes is, why is that a challenge, right? Why is Hounsfield units, different Hounsfield units, a challenge? So for you to understand that, normal technique that we follow in almost all data science problem, of when you have a wide range of units, is normally you scale it down, right? For all kind of deep neural networks, you normally scale it between 0 to 1. Now, in case if you do a scaling like that, where you are trying to scale down from 3000 to 5000, so you would be dividing almost every pixel value by a 5000 number, right? So what that primarily results is that the difference between, there's a very subtle difference between, for example, if there's a bleeding in the brain, right? The area that you see here. So this is a hemorrhage in the brain, and then there's an area which is slightly just outside that hemorrhage, right? Now the difference between them is somewhere between 65 to 95 Hounsfield units, and the gray matter outside that is say 40 or 50 Hounsfield units, right? So in difference, there's a Hounsfield units is just probably 10 units separated, right? Now, if you divide that by that huge range of 5000 Hounsfield units, the difference between those tissues suddenly is reduced to somewhere around, in the subtle parts that you see here, is would be reduced to almost 0.003, which is extremely difficult for radiologists, or for AI systems to pick that difference up, right? So that's the other big challenge of um, in having Hounsfield units which go from all the way to minus 2000. So your normal normalization techniques that you do sort of might not work directly as you would expect them to be. So that's the second problem about medical images and the way they're very different from natural images. The third is actually my most favorite. So what happens in normally if you're building natural images based AI system is that it's very easy for you to debug images, right? You have trained say an algorithm to detect a dog, let's say, right? And if the AI system is not able to detect that dog, you can very well easily say, you can see where the AI model is making that confusion. You can understand what's actually causing that confusion. Is it bad quality of image? Is something else which is crowding in the image? So it's very easy as someone building that system. It's very easy for you to debug that natural image based AI systems. Whereas if it's for actually for medical images, it becomes increasingly difficult, just because, for example, if you're someone with a not a medical background like I and most of the people working in this field, you do not have a background of medicine as such, right? You have done something in a computer science major, and then you join this thing and you try and build this. Now, if you don't have that understanding, it's very difficult for you to build these systems and specifically debug them, right? So, for example, on this part of left hand, you see two images of the head. So one is an edema. Edema is basically a swelling around. If you have a tumor or any kind of other brain trauma, you normally have a swelling around that piece, which is called edema. And then there's something called infarct. Infarct is basically a clot in the brain, which normally shows up as stroke, right? Where basically a part of an artery has ruptured and the blood flow to that part of the brain has completely stopped, right? So that's called infarct. And in essence they both would look like the same, the way you see here, right? So one is which is they are completely dark as opposed to the rest of the brain part, and it's very easy to actually, I mean, for human beings to difficult that, it's actually very, I mean, it's already a challenge. Now imagine and asking an AI system to differentiate between them, right? Where they're actually very similar, it's just a dark region in the brain, right? That you see. So that's the first part, right? So that's one kind of challenge, which is understanding and differentiating between different medical terminologies. The second part is, chest X-rays, for example, right? These are both the examples that you see here are completely normal chest X-rays. Both the X-rays look, I mean, in terms of a clinical evaluation, they're absolutely perfect. But if you look at them, they just look extremely different, right? I mean, one where you have a complete black, this part is completely black, right? So this is the difference is primarily because how you have taken the chest X-ray, the exposure that you have given that X-ray. So that's very different. So that's primarily the one which is causing the chest X-ray, to look so different. So that's the reason that you would see that, even though the chest X-rays look very different in terms of clinical evaluation, they are completely fine. So these are both normal chest X-rays. the the next challenge that you see here is primarily around how do you build such medical imaging AI systems, right? So in case of natural images, um, you have already your pre-trained models, and there are huge data sets which are available, right? So for example, an ImageNet, and there's bunch of those kind of data sets as well. But uh, to build some of these AI systems and huge data sets, in fact, uh, and in almost every natural imaging problem that I've ever worked on, you never start the models from scratch, right? You always have this pre-trained ResNet model or something else which is already there, and you actually build on top of that, right? If you're customizing it for a problem. Unfortunately, in medical imaging AI, that's not the case. It's You do not actually have this kind of pre-trained model. Firstly, so every time you are training for a different body part or a different CT or an X-ray, you actually have to start from scratch, and that's a challenge, right? I mean, if every time you're trying to do from that, so every time your models, all the issues that you have with like starting from scratch, right? Initializations all the way to how quickly the model converges, all of those challenges become a profound problem while you're doing medical imaging. And on top of that, if you do not have such huge data sets, open data sets that you actually have with natural images, that just makes your job as building that data science AI system altogether much more difficult. Um, so that's a huge challenge, I would say. And finally, I think the last challenge which I wanted to just touch down on, and again, is something which is extremely unique in medical imaging. You do not normally see that kind of those kind of challenges in natural images, is something called as a radiologist hedging. So while radiologists report, so to understand this, let me just give you the context. So when you're normally looking at medical images, you are trying to build your ground truth by looking at the report of a radiologist, right? So whether the radiologist has called that as a particular abnormality or not, right? So you're looking at that report and you're making that final output where when you're training, your data set label is decided based on that report. Now, what happens in case of real life and real life radiologists actually reporting is that uh, they are actually also human beings, right? So when they see something where they're not able to actually decide for sure by themselves, they would mention things which are, where they actually hedge themselves. They do not also want to call out something where there might be, legal repercussions on that. So they don't actually say that out explicitly. So, for example, they would say something like, "There's a diffuse cerebral atrophy," and then they would put a question mark on the end of it, right? And obviously when you and idea is that obviously a radiologist is looking at the image to just make that conclusion, right? Uh, and when they put a report like this, the idea is that the physician, right, the one who's actually facing the patient, when they meet the patient, they can actually ask more questions to get these doubts resolved, right? So in a real life setup, this works perfectly fine. Even if something like a suspect lacunar infarct, you can actually question the patient and you can understand what, the clinical history of that patient. And based on that, when you finally give the diagnosis to the patient, you can resolve some of these doubts. Now, for an AI system, unfortunately, when you're training just based on an image and then the report of that radiologist, if you do not have a clinical history of that patient, that becomes extremely difficult for an AI system to, tackle some of these things, right? So where the radiologist is not completely uh, explicit in their diagnosis of that thing, so diagnosis of the abnormality. So that becomes extremely difficult for a radiologist, for an AI system to pick that up and tackle that as a challenge. So that's an interesting bit which actually happens only in medical imaging as such, if you think, right, where determining the exact ground truth for the particular image becomes a challenge. And obviously because there's a clinical history which actually goes in for making a decision, right? If you do not have that clinical history, then you're actually you're not you do at a disadvantage, right? You're trying to make a diagnosis based on just an image, whereas in real life you get more data points actually to make that decision. So yes, so this is primarily all the challenges that we face, right? So all the different, when we started solving some of these problems, these are different challenges in terms of, how, you know and specifically at that point, right, when 2015, 2016 you got started, uh, you do not have that kind of I mean, today obviously the community is way more spread out, way more open. There's a lot of research that's going on, and there's a lot of it open source as well, and a lot of people to actually refer to. But back in the day, uh, yeah, TensorFlow was definitely not there. You had to code on things like Theano. I don't know even if some of you would have heard of it or not. So yeah, it was back in those days. You were trying to look at AI for medical imaging, where obviously a lot of these challenges were completely something we, in a way, dealt it for the first time, right? We did not know how to go about them. But because we did that, that's added to our learning of how we actually tackle problems. Um, so in terms of learnings, I think there are three major things that I want to address and want to talk about, for everyone who's actually planning to build this out. There are three major issues which I think, which are absolutely key. And I'll so obviously if I just mention if they're key things to do, you probably might not be as enthusiastic to pick them up. So what I'll do is, for each of these three things, I have a story that I wanted to share with all of you, that might actually, make you appreciate the beauty of doing all these three things. So the first one is around interpretability, the second one is about learning medicine itself, and finally is about elegance and, sophistications that you can do in algorithms. So those are the three things which I think, as someone, if you're starting out, or even if you're not starting, when you're already doing AI in medical imaging, I think those three things should ideally be something that you would have to build yourself and build a skill set for that yourself. So without much further ado, I'll just go into each of these three things that I want to talk about. So the first is interpretability, right? So interpretability, the concept is that, what do you mean by interpretability is the idea that if you have an AI system which is looking at if it's specifically in a computer vision problem, the idea is that the AI can look at a image, it is making a decision, and you have to somehow attribute that decision back to the image, right, on based on which it has taken the decision. So if you're seeing that, if you're looking at an image and you're trying to predict if it's a cat or a dog, and if the AI system predicts it's a cat, then you have to actually flow it back to the main image and identify which part of the image was responsible for that AI system to make that decision. So this is in terms interpretability. Obviously, for every one of you who's been involved in this space of deep learning and AI, you would understand interpretability is definitely critical. But in medical imaging, that plays out a huge role, and I'll tell you why. So the most important thing that you have, and the most important reason why you should look at interpretability is because in medical imaging, you are actually dealing with the health. I mean, you are actually dealing with a critical piece of diagnosis, right? Someone is a radiologist or someone else would be looking at the AI systems diagnosis of that medical image, the interpretation of the medical image, and making a decision based on that. Now, it's since it's so critical, right? So radiologists, when they use AI, obviously they want to understand if the AI is making, if AI is looking at a chest X-ray and it's calling out to have a, say, an abnormality like a lung nodule, um, or something else, right? So it would obviously want the AI system to mark out exactly which part of the chest X-ray made the AI think so, right? So that's very critical. That's very important if you think from a end user perspective, right? A person who is using the AI system, they obviously want to know why the AI system is making the decision that it is making. Now, the problem that happens is obviously this is something which, while you're building the system, you do not care so much about what the end user wants to get out of this, right? So you want to build what you want to build. Now, so that's the reason why I always say this, that forget about building an interpretability for the radiologist or the end user, whoever's using this AI system. Build interpretability just because of the fact that debugging is difficult. I already told you about that earlier, right? Debugging is very difficult, specifically if you're not someone from a medical background, right? If you're from a computer science or any kind of background like that, you have no idea of what is going on in the model, right? You have no idea if it's making it looking at a chest X and it's calling out something. You have no idea of figuring that out, right? And the only possible way you can actually do that is by actually building interpretability as part of your pipeline, right? When it predicts, you can look at a false positive or a false negative and you can understand what's going wrong there, right? That's, I mean, without interpretability, it's just extremely difficult. I mean, specifically for classification models. I mean, semantic segmentation or an object detection, anyways, comes with an interpretability that is built into the model. But in case you're building classification networks, interpretability is absolutely important. That's something you need to definitely take care of. So that's the most important thing. Now the story. Now is the most interesting part. So this is a story back, I guess somewhere early 2017 or somewhere. So we were looking at, we had just looked at an chest X-rays, which we had built our first, I think, first iteration or version of the chest X-rays, and we had trained it. I forgot on some amount of very small amount of data, and we thought that we have already built it. We almost had a somewhere around, I think, 97, 98% area under curve classification algorithm, and we definitely thought we have hit the mark, right? And this was early 2017. And then obviously we were asked to sort of deploy this in a live setup, right? And where someone would actually use this to make a decision, right? And we thought that this is perfectly fine, right? The thing that happened was, unfortunately, uh, when we deployed it in a live site, we suddenly saw the accuracy go down from 98% to all the way down till somewhere around, I think, 67, 70%, right? And we were suddenly wondering what happened, right? Because obviously we thought we had built a very accurate, very perfect real life AI system, which actually can look at a chest X-ray and classify different abnormalities. But when we tried looking at what actually happened there, so what we understood was an interesting thing that had happened, which is a lot of the training data that we had was primarily collected from hospitals where you had patients in ICUs. And what happens with patients in ICUs is that you do not, they are not able to move a lot, right? So you take chest X-rays through some machines called portable chest X-ray machines, right? Because you're not able to make that patient. So the patient is on the bed, they're normally lying down, and you have this portable chest X-ray machines to look at those patients. So if you look at some of those X-rays, what happens is they have this portable marking which is written on those chest X-rays, right? When you have those patients from an ICU setup. Another thing to understand also, that is when you're normally looking at ICU patients, they're almost always critical patients, someone who has already some kind of an abnormality in there, right? So it's a very easy correlation to have, which is that everything that is portable chest X-ray is ideally likely to be abnormal. And when we actually tried and understood what was going on, it's exactly that, right? The chest X-ray system has started making that correlation that everywhere you have a portable chest X-ray being done, that's likely to be abnormal. Now, in real life, that's not the case, right? Because in real life, you can also have this portable chest X-ray, otherwise also taking patients taking chest X-rays on that. So that becomes a real problem, right? When you start to take this out right now. If you, and obviously once we had this problem, that's a point of time where we started building interpretability as part of the system. And if we had obviously had that interpretable AI system beforehand, we would have figured this out before doing that deployment. But yeah, that's a lesson learned, right? That's why so critically, and always suggest people who are building specifically classification systems in medical imaging always build interpretability as part of the network, right? So this was the first story where we learned how interpretability is very critical, and specifically if you are, and this is not just the first case. I mean, I don't know if rest of the stories we cover that, but other places also where I have been stuck at a problem and I'm figuring out what's going wrong. I have to decrease the false positive or decrease the false negative. It's very easy to understand that when you have an interpretable system like that, you can very easily figure out what's going wrong, where it's actually looking to make that decision, right? And you can check and understand it with the radiologist. You can actually then do pre-processing or whatever, how you change the architecture, but you can do a lot of things once you understand what's going on, right? So that's the first important lesson. The second is something which, again, a lot of developers, I would say, do not like the idea, which is about learning medicine, right? And this is something I have stressed. Whenever I talk to people who are building AI system for medical imaging, I stress on this a lot. That you have to understand what is medicine, right? And without understanding that, there's no AI in medical imaging, right? So interesting thing, and again, I'll tell you stories so that you understand what is the importance of doing that. So I already explained you the problem of CT scans, right? Where you have uh, scans having Hounsfield units going from minus 2000 all the way to 5000 Hounsfield units, right? So that's a range of 3000 Hounsfield units in which you're looking at. Now, obviously, if you normalize them between 0 to 1, that's almost never going to work, right? Because the difference that you're planning to pick up, right, that between a something which is a bleed versus the region around that, so that difference would boil down to 0.0003. I don't know. It was a very less difference if you remember, right? So so that's obviously a challenge. So the question is, how do radiologists do it? And if you understand that, then you will understand that when radiologists try and look at that, they actually use a concept called windows and levels. So windows and levels are basically the idea where you are looking at a window, say window width called W and a window length called window level. Now you have an upper limit which is window level plus window width by 2, and lower limit which is window length minus window width by 2. And then you basically say that everything that is less than that particular lower threshold, right, that value becomes equal to the lower threshold. So if the lower threshold is a 0, so everything which is less than 0 Hounsfield units is equivalent to 0. You make that pixel value to 0, and everything, say the upper threshold is say around 100 Hounsfield units. So everything in that image which is greater than 100 becomes 100, right? So basically what you did in essence is basically take everything above 100, normalize that to 1, take everything which is less than 0, normalize it to 0, and then you're just able to focus on that range of Hounsfield units which is just between 0 to 100, right? And 0 to 100 is normally not the standard one. So the standard ones, like for if you want to visualize a brain, right, so you take the level at 40 and you take the window width at 80, right? So your upper threshold is somewhere around, I think, yeah, around 80, and your lower threshold is 0. So that's where you get, if you do that, you get a brain window. If you want to do a bone window where you're primarily focusing on the bone and the skull as such, right, and you do not want to look at what's going on in the tissue, so you then choose something where you have a window level of 480 and your window width is 2500, right? So yeah, I mean, the idea is that there are different ways. So based on which part of the brain you want to focus on, you have different windows and levels. And that's an interesting thing, right? And that you do not know until you actually study medicine, right? Until you actually understand what a radiologist is doing and how they are doing it, right? And these are things which are absolutely normal and absolutely commonplace for a radiologist to understand. But if you're someone who do not have that background in medicine, right, you just wouldn't figure this out. And if you go about this, as I said, I mean, the normal process of normalizing, that would just never work, right? So this is a very interesting story. I mean, when you learn some of these things, you just amazed at that. Yeah, there's all of these things which are already existing in medicine. Right? Why don't you just leverage that? That's a question. There are two more concepts which I mean, it's very interesting concept. These are not, I mean, rocket science concept, but yeah, I mean, if you know them, your life becomes a lot more easier. So the first one is on the left that you see of symmetry of body, right? So lot of body parts, right? You do a scan, they are completely symmetrical, including the brain as well, right? So there's a lot of things that you can do around, trying to understand when you actually, how do you pick up the abnormalities? A lot of times it's just contrasting it with the other half, right? So for example, in this case, you can see there's a abnormality that you see here, which is not here, right? So this part of the lung. So that's a very easy thing to pick up when you understand some of these concepts, right? That's the first. I mean, when you're starting out, from a computer science background, you're trying to understand medical and medicine as such. This is very easy way for you to understand. Okay, there's something definitely wrong here, right? So those are interesting things, right? And these are things that you can leverage as while building your models as well, right? So that's one concept. The second concept is very interesting, and again something which is absolutely common knowledge, which is that when you have an injury, right, and specifically if you have a head injury, what happens is if you have an injury at say some part of the brain, normally there's something that you will also develop. So if you have a bleeding say around this part of the brain that you see here, uh, or swelling that you see, so exactly diametrically opposite part of the brain you'll also have something which would be a bleed or something, right? So when injuries normally happen, they would basically happen in pairs of diametrically opposite points, because the skull is a fairly solid substance, right? And the brain is very liquidy jelly like, right? So obviously if there's a repercussion at any part of the brain, you would normally have something which would also show up on the exactly opposite, diametrically opposite one. So this is something which is called contrecoup injury, where although you have a repercussion here, but you will normally see something which is exactly opposite part of the brain. Also, so that's again, that's a concept that's fairly common. Any radiology, any medical student would definitely tell you this. But if you don't understand medicine, if you don't learn this things, you do not know some of these things. And I'll tell you why this is important. The next story is actually about why knowing some of these things helps in actually building solution. But yeah, the first part is obviously you have to know these things, and for you to know these things, you have to understand medicine. You have to learn medicine. You have to understand anatomies to a good extent for you to build something, right? Because you cannot just be excused for not having that background. That's very critical for you to build something. And now the third part and the final piece of the story, which is elegance, is important. Elegance, when I say elegance, the primarily idea is that I'm trying to look at sophistication slash hacks, if I would call it, as opposed to just more uh, computation heavy or more uh, deeper networks. So I definitely am a more proponent of the view that a lot of times the elegance is actually what, how you solve that problem, how you actually structure that problem is more important uh, than how, what kind of different architectures that you can do and what kind of different loss functions that you train on. So while yeah, some of those innovations are absolutely important, but a lot of times it's important to just do that in a more elegant way. And when I explain you the story, it would be easier for you to understand what I exactly mean by elegance. So to do that, obviously, I have already explained this, what CT means, which is basically a stacking of multiple 2D images of different parts of the brain that you do. And this is how it looks like in real life, right? So this is a 3D image, as I mentioned. In case of CTs, as I mentioned, they're normally a single channel image with Hounsfield units going from minus 2000 to 3000. In MRIs, that those are almost five to 10 channel images. But yeah, in case of CTs, as I said, it's 2D stacked images, 2D single channel images stacked on top of each other, and this is how it looks like, right? Now, we were trying to build the problem of detecting fractures from head CT scans, right? CT head scans. This was again story back in, I guess, somewhere in early 2018, somewhere around that time. So the challenge we had was the problem we had to solve was primarily detecting fractures from non-contrast CT heads. Now, detecting fractures is I mean, it's an extremely difficult problem, and I'm just again going to give you a slight overview of why that is a problem. So what you see as fracture is this particular thing that you see here, the one that I've highlighted here. So this at best is around, I mean, this single straight line is probably 2 or 3 pixels wide, right? And imagine this in a stack. So you're now looking for those 2 or 3 pixels primarily. in a stack which is of say 512 plus 512 plus 128, right? So normally there would be 128 slices. So out of those 128 slices, probably 2 or 3 of them are actually gonna have this kind of a 2-3 pixel wide line, right? So this is actually almost close to a line that you see here. Right? So you're trying to just detect that line among huge bunch of slices of that image, a 3D image, right? So it's almost equivalent to looking for a needle in a haystack, right? So the sparsity problem, right? So for anyone who's aware of class imbalance and all those kind of problems, right? So sparsity in this case was 10 to the power minus, somewhere around 10 to the power minus 5, which is an extremely imbalanced class imbalance problem, right? So that's the first layer of difficulty. The second layer of difficulty comes from the fact that there are a lot of times what you have in the skull is primarily joints, right? So there are different joints in the skull, which are called sutures. And what you see here is there are those sutures also primarily look like straight lines that you see here, right? So there are a lot of those kind of joints between them, and only one of them is actually a fracture. So the fracture is primarily where something is broken, right? But that would look like a straight line as you saw in the previous example. But also what happens is anytime uh, the two bones are merging, which is normal. Those are something which you call as sutures. So sutures are completely normal and they are present in abundance, right? So in particular scan, you can see a lot of those kind of straight lines that basically are intersections of two bones. So that just makes your difficulty, I mean, the level of difficulty a lot more higher, right? Because now you're looking not only for a straight line, but you're also looking at a straight line which is different than the other kind of straight lines that are normally supposed to be there, right? So this has to be a straight line which is in an unusual place, right? So that's the difficulty, level of difficulty suddenly increased. Now the third problem is fracture in themselves, right? Those 2-3 pixels, although I mentioned it as straight line, but the straight lines can look very different, right? So something like a depressed fracture where the bone is pushed inside would look very different like this, where the bone is actually, you can see there's a compression that here, versus an undisplaced, where basically the bones have not been displaced, right? So they are actually just in there, but you have just developed a single line of fracture. And comminuted, where basically the part of the bone is just pushed inside, right? So that basically now I've broken it down into 3 parts, where a small part is now pushed inside the brain. So yeah, medical terminologies, but again, it's very important to understand that the fracture problem itself is extremely difficult, right? Just to detect a fracture from a HCT scan. So the idea was, I mean, and again, I mean, we started off with this problem. I was looking at it. I think first I spent almost, I think, 2 or 3 months on this, and the accuracies were just around 67, yeah, somewhere around that range, 50-60% area under curve, right? And this is just not working, right? And I was completely at a loss as to how you deal with this kind of a problem, right? Because I just can't make sense of this problem because it's just incredibly difficult at so many layers, right? So that's when we started looking at how does a radiologist do it, right? And how do they actually do it? And what we understood was, if you remember my last conversation, which is that so radiologist I was talking to, he said, Rohit, look, you're doing the problem completely wrong. As a radiologist, how you look at it is very simple. You would normally only develop fracture when you have a trauma, kind of a road accident or something like that, right? And if you have a road accident, you normally always would have an internal bleeding in the brain. Now, the internal bleeding is very easy to pick up, right? As you can see here, right? The internal bleeding is a white thing, it's swelling, it's very easy to pick up. But the fracture is always either at that location or something where it's diametrically opposite, right? And once you know this, your life becomes a lot more easier, right? Because now you're not just looking for the skull fracture independently, right? Now you have a tool to say that, okay, so if there's something which is somewhere there's an internal bleeding or something, it's easier to actually trace it back from there rather than just searching through everywhere. So that's an elegance, right? That's somewhere, that's a, firstly it required medicine knowledge for me to do something like that. The second part is it's an elegant solution. You're not just brute forcing your algorithm through a bunch of data and trying to get to the solution. So that's the solution that we developed, which is primarily the fact that, just give me a, so the solution that we developed was primarily around the fact that, so now there are 2 parts to the algorithm. So first part, which is just classification, which looks at a brain and it detects other portions, the probabilities for the bleed in that brain. And then there's one part which is just looking at fractures and straight lines that are there. and then you primarily combine these two networks to finally get the actual probability for the skull fracture, right? And this, as I said, I mean, this is not a rocket science, right? I'm this none of these networks are like extremely big networks or completely sophisticated, completely different networks. It's about how you structure the problem, right? That is just, it's not very different. It's just but just a lot more elegant, and it just leverages something that radiologists or human beings have already been doing to come at that decision. So this is very key thing that I ideally always want to share with someone who's specifically working in an AI in medical imaging field, that you need to understand how to build elegant solution rather than just trying to brute force your way. This is very important for you, and for that, obviously, the second part of what I mentioned, which is you need to learn medicine to some extent, right? You need to understand anatomy. You need to do that. So this was obviously this got published back in 2018, which was in Lancet. Lancet is globally one of the most prestigious medical journal worldwide, right? And this was India's also first AI publication that got published in such a prestigious journal, right? And Lancet also globally, this was the first AI in medical imaging publication that was published in the Lancet back in the day. So yes, this was a proud moment for us, and obviously, I mean, as you understand, this is something which is not very difficult, not rocket science, but something which is very easy to do. And this is it. I think this is the final part of the session. So these are some of the websites where you can get some open databases if you're someone who's right now they're planning to get started. These are some nice places to get started off, so you can take screenshots and absolutely use them. And that's about it. I think if you're planning to get started, this is not a very difficult place to be in. You just have to put a bit of effort. You have to just think a bit differently than you would think for a normal computer vision problem. But yes, absolutely. And these are finally my social network. Uh, I would say so. I'm trying to be a lot more active on LinkedIn and Twitter these days. Uh, I don't get time as much though, so I have a lot of people who reach out for me, in terms of understanding how to solve some of the problems. And obviously, I mean, solving a problem is not as easy as just looking at something and giving it. I would need to understand some of those things in full detail. But yeah, I have been trying to make a conscious effort to help out as many people as I can. So that's my LinkedIn and that's my Twitter ID. Feel free to connect with me. I normally also share some thoughts around, how to publish papers, how to do some of those things. So always happy to stay in touch and reach out to me in case you have any questions in medical imaging or otherwise as well in as such AI and data science. So I guess that's primarily in terms of the session that I wanted to talk about. I hope this was something which was insightful, something that you could take something back from here. Happy to answer any questions that you have right now. I'm looking at the YouTube chat. I'm not able to see any conversations. I think that's the YouTube is the best way to sort of redirect questions if you have. Uh, I'm not able to see any questions still there. So if you have questions, just type it out there and I can probably explain it. I think I just see on the chat there's just one question that I see from and not chat question actually. I see just one link of hi from Nandini. Uh, yeah, I guess I'll wait for a couple of minutes in case you have questions. Or again, Usha, feel free to suggest if there's some other way we can take the questions. I'm eagerly looking. Usha, just step in if you have any suggestions. Probably we can end the session in that case here if I don't see any questions coming in. So yeah, let me know your thoughts. Okay, I just saw this someone who pinged me on LinkedIn saying there's a lot of questions I'm not able to for some reason. Let me just see. Um, okay, I just well still don't see live chat. Let's see. Okay, I see a lot of questions now. Okay, okay, great. I suddenly now I was not able to see anything beyond hi.
Yeah. So Rohit is the okay. Are you able to see the questions, or you're not able to see the questions?
I'm now able to see. I mean, for some reason, I just was this live chat was stuck at Nandini's high long back. So yes, I can see. I can probably would be. I'll go through some of the questions. I'll start taking from top. So the first
Yeah.
question was, how did you learn radiology being a computer science guy? Funny, but I had to read up a lot of. So there are a lot of medical texts out there. There are a lot of open websites like Radiopedia and bunch of those kind of things. But I still remember an interesting story. Very early on in the day, I actually I had this got this text which was anatomy of medicine, right? I mean, very basically they cover different body parts and do that. This is actually full course, but yeah, I had to. You have to do that, right? I mean, so definitely there are on site. There are definitely online lot of free articles where you can get started. But you also have to put that effort and go into depth. Obviously, it's an ongoing thing, right? I'm still learning a lot about, for example, COVID, right? I have a, I think, obviously, as someone who's completely from a technical background, I have a very good understanding of how COVID happens, what's exactly how it works, and when you look at a chest X-ray, how you detect what you detect. So it's an ongoing process. You learn more and more as you're in the process. So that's definitely there. So that's the first question. That was from Sai Sritej. I hope that helped you understand Sai. The next question is in considering the channel's complexity in hyper. So this is from Nandini. In considering to the channel's complexity, RGB using hyperspectral imaging wouldn't solve the complexity. Uh, it would depend. I mean, as I said, I probably explained your question while going through the presentation later on. There are multiple ways you can challenge the question. I mean, you can address that challenge of different channels. And yeah, absolutely, hyperspectral imaging could also possibly work. Although I have not tested it myself, so I'm not very sure. But yes, that's definitely there. The next one, I think, is, can you please suggest a path, a roadmap for beginner to gradually take a career in data science slash AI in biosciences field? Ah, interesting. So I'm not sure if I normally don't believe in giving out a prescription based thing like, do this that and you will get there. I genuinely believe that everyone has their own journeys, but I can still give you some kind of pointers as to what all things work for me. As I said, obviously first part is, yeah, if I'm guessing that you're already someone who's probably, obviously you need to understand first data science is the most important thing, right? You have to understand the exact mathematical understanding of machine learning, how it works, how support vector machine, for example, works, or what is support vectors, all of those things, right? Uh, Understand machine learning very, that's the most basic thing, right? Once you understand, then you go into deep learning, understand that well, understand the mathematical rigors of math. I mean, I normally focus a lot on mathematics and statistics piece of ML and AI because that's very core to understand and debug. Again, debugging is very critical, and to do that, you need to understand what's a piece to focus on. So that's the most important thing. Once you do that, I would then suggest, obviously, if you're focusing, as you said, on biomedicine, biosciences field, then you obviously have to read up on bit on medicine and understand which part of it you want to focus on. So I focus on, for example, what I told was about AI in radiology, but there's AI in pathology, there's AI in bunch of things, right? Monitoring ECG patients. There's just too much which is in AI in healthcare, right? So you have to then understand which part you want to focus on, then take your path from there on. So that's my suggestion. The next one is, so ResNet can't be used. Also, normalization does not modify the images such as it makes difference. Absolutely agree there. So yes, ResNet can't be used. I would not say it can't be used, but your pre-trained ResNet definitely can't be used. So that's, hopefully that answers your question. You have to definitely train something from scratch. The next one is, which one gives high accuracy to detect tuberculosis using chest X-rays, DL or ML? Um, Obviously, deep learning works better than ML, specifically for computer vision problems, if you are able to work them out. Although I normally, if you're asking for a general statement, then obviously I think you always start out from ML and then you go to deep learning. That's normally the process I suggest to everyone who's solving any problem in AI. It's easy, just start with basic things, then you go. But for tuberculosis and specifically computer vision, obviously we have seen now that deep learning systems empirically perform much better than machine learning. So that's, I think, for if you're looking at specifically TB in chest X-rays, that's one of the major problems we also have been solving. I definitely would suggest deep learning. The next question from Dipanshu is, what happened to Thiano? Yeah, I mean, I also don't know what happened to Thiano. Yeah, it's a sad thing. I mean, I'm not sure if it's sad. I mean, it was really fun those days, but yeah, it's not anymore. And I think it's for good. I think we have PyTorch and TensorFlows, which looks obviously much better than what Thiano, or there's something else, also Lua. I mean, Torch, right? Torch itself before it became PyTorch. So the next question is, how to identify noise in medical image. Uh, yeah, it's. I would say Vikrant has also answered that perfectly fine. I think it's very difficult to do that, and you have to again understand medicine to understand exactly what is noise for medical imaging versus what is not. The next question is, how to make large data set for tuberculosis. What is a typical training for data set size? I think I'll answer both the questions normally. uh, I think it was probably aimed at Sudarshan, had specifically aimed for Bala, so I think he has aimed that. Uh, Question was, I think someone else asked, will we have any hands-on session? Answer is, unfortunately no for this session, because two things. I think, and I have some recordings for our hands-on sessions which are there on YouTube. If you want to check them out, it's easier for you to understand that. There's YouTube, there's Grey Atom channel, which primarily where you would have all of these things. And apart from that, you would also have some. I have specifically done hands-on for chest X-ray for I think pulmonary, some kind of a specific abnormality. I forget that. And there's a hands-on session video which is there on Upgrad. I think yeah, that should also be freely available. So I think, yeah, I did not want to specifically spend time on hands-on sessions because those are already recorded videos that's out there. Uh, Could you share the links for datasets? I think already that's again an ongoing internal conversation. What platform is best for development? What platform is best for development? TensorFlow or PyTorch, whatever is easier. Obviously, I started earlier back when TensorFlow was obviously not that developed as much. So I had started with PyTorch, but I think today TensorFlow and PyTorch are almost equally. And obviously, if you're starting out, it's better to start on TensorFlow because TensorFlow is a lot more. Um, I would say the community is much bigger right now. So if you're starting out, that's easier to do that. I think there's a lot of people asking dataset, open dataset for ultrasound, open dataset for other things. There are lists of some open dataset which I shared towards the end. Happy to, if you have specific thing that you want, happy to answer that on LinkedIn or Twitter if you reach out to me specifically for. Uh, do you think the need to register with regulatory body for AI experiments? Absolutely yes. I did not want to cover that because that's a lot of the business side of things. But yes, there's an absolute requirement for any AI company, which is, I would suggest if you're looking at building something which is an AI company itself, uh, definitely start focusing on how to do the regulatory because that's critical. You need to be CE or an FDA approved for you to actually be selling commercially any of the AI systems. So that's something you should definitely work towards. For doing experiments, as long as you have the proper ethics approval from a hospital and all of those things are in place, it should not be a problem. Or you're working on open data, that's fine. But for any time you're working on something where you do not have an ethics approval or you do not have others, and you obviously cannot use the system in real life without a proper regulatory approval. Yes, how funding is achieved. David asked that. Funding, David, is a interesting question. I don't think makes a lot of sense to discuss in detail, but obviously in a TensorFlow user group meeting. But I think the idea is primarily that if you have a product and you can show a commercial traction for it, there's definitely a problem and there's a value that you can generate using the AI. So that should definitely help you leverage funding. Uh, Someone else is, there are a lot of questions which I see now on funding. There's one from Swati as well, which is primarily around funding. Yeah, I think for if you're so I think there's one part which is if you're an AI company and you're looking for funding, that's the answer I did. Also, the other piece is if you might be asking that if you're someone who's wanting to build something or do you want to have some data set collected, all of that, how do you get funding? I think that probably would be dependent on there are a lot of people who are giving out grants, specifically a lot of TB eradication or any other places which are giving out grants. So look out for the grants and obviously any of the research institutions like IITs, I think triple ITs, they all have a fair bit of funding which is reserved for this. So if you're trying to get paid for some of the AI problems that you're doing, you might as well approach them. So fine, again, is there any open data set for I think uh, the next one was I was working on diagnosis of COVID from chest X-rays. Medical is something which is stuck up. So anyone who's stuck up on things, absolutely reach out to me. The next question is, does radiomics methods include deep learning model methods? So that question I'm not very sure. So radiomics is primarily the idea where you're looking at quantifying different parts of the medical image, and you're trying to from there get a correlation of how the patients actually progress, right? So so there are two parts of the problem, right? First, identifying which part of the brain is affected, and then from there relating it to the clinical progression of the patient. So both those pieces could ideally do. The first piece definitely involves deep learning today. I see a lot of research papers which are focused on radiomics in part of detection, but I think for clinical correlation between the radiomics features to the patient outcomes is normally more of machine learning methods. So this was very much detailed. I think Swati, you asked, so I think it's specifically for you. The next question is, which one would you suggest any particular image processing books, resource for medical image processing? No, I don't have anything in top of my head. Yeah, for medical imaging, I don't specifically have. For me, at least the journey, as I said, explained to all of you, is more of AI first. AI was independently, and then medicine was independently. Right, I understood medicine, reading up on radiology specifically. So yeah, I never found anything which is which talks about both of those things in a simultaneous way. The next one is, which one is better, Swati, again, TensorFlow or PyTorch? Tough to call it out. I mean, for me, obviously, I've been a lot more involved in research, and as I said, I mean, it started with Piano. There was something else also in between it. Kind of forget about it. There's some other network, other language, and then I switched to PyTorch because at that point of time, Torch was Lua based. Before that, 2017, I think they went to PyTorch, and yeah, so I've been using PyTorch since then primarily a lot because I mean, at that point of time, TensorFlow had a lot of documentation issues and all of that. But I think today, TensorFlow is at a much better place, and I have been part of ML. I mean, the GD group. I have been part of that feedback process as well. So I think today TensorFlow where it stands, and if you're someone who's starting out, I think it's almost hands down. You need to use TensorFlow. Obviously, if you're someone who's already involved and you do need to do a lot more uh, fine tuning and a lot more sophistication, like you want to flow back gradients, you want to sort of inspect gradients at a very different levels. I think those are some of the things which I at least found PyTorch was useful for. But again, I mean, today I'm not very sure how difficult or tough that is. Uh, yes, so I think Dipanshu also mentioned that it's PyTorch is research papers actually have which research a lot of times is actually on PyTorch. It's less on. Uh, yes. So finally, one is can you send us a link of hands-on sessions? I'll have to check. The Grey Atom link, I'll definitely post it after the session ends. I'll post the link here. And yeah, I think that's about it. I think that's how do you think chest X-rays are reliable for diagnosis of COVID-19? And there's one more final question. I think those are the two questions which I'll take for the day. So the first question is, how do you think chest X-rays are reliable for diagnosis? That's I think depends. Chest X-rays definitely for asymptomatic patients is a very important tool to pick up because in specifically countries like India, where we are working with Bombay municipality, for example, last 3 months, right? We have been working with Bombay municipality where they take mobile X-ray vans and screen a lot of patients. The point is, if you have limited number of test kits, how do you decide which patients gets to be tested right now versus who gets tested later on? And to do that, chest X-rays, specifically for a resource country and country like India, it's the most important way. So absolutely, again, Sagari, happy to discuss on this if you have more questions. I think Usha wants to probably wrap this quickly. The final one is, would you suggest any online course for medical imaging? Again, I'm not sure. I've seen one course from fast.ai, I think, some time back. I've not myself had a look at it, so can't comment on that. And as I said, for me, it was primarily medical was one part of learning and imaging and separately. I have at least done that, but yeah, I think I'll definitely once I get to know fast.ai, I think I'll let you know. So I think that's about it. So thanks a lot everyone for really asking detailed questions. I'm more than happy to engage with all of you on LinkedIn and Twitter separately to discuss some of these things.
Yeah, thank you so much, Rohit, for a very interesting and engaging session and for also patiently answering everyone's queries. And for the audience, thank you so much for coming and joining us on Sunday night. And we're conducting at almost 3 to 4 events every week. So do watch out for Vimal DS Mysuru, TensorFlow User Group Mysuru, and GDG Mysuru events meetup page. And next week we have masterclass sessions on transformers and attention models. Don't miss out on that. Also follow me at Rangaraju in Twitter to be notified of the events. Thank you so much. One more important thing is we'll not be having the second session for tonight because the speaker couldn't make it because of unfortunate circumstances. So that will be postponed to a different week, which we'll be notifying you later. And thank you so much, everyone. And thank you so much, Rohit, for joining us. Looking forward to host you again in future. Thank you.
Absolutely. Thank you. Thanks, Susha. Thanks for doing the wonderful event. Kudos.
Yeah. Yeah. Thank you. I'm ending the broadcast now.